Let's explore the 20 levels of quantum physics. Level 1. Atoms and particles. Let's begin at the very beginning, with the most fundamental question: what is everything made of? Everything around you, your bed, the walls, the air you're breathing, the stars shining light years away, is made of tiny particles. These particles are so unimaginably small that millions upon millions of them could fit on the period at the end of this sentence. We call these particles atoms. Atoms are the building blocks of everything in the physical universe. Your body contains about 7 billion atoms. That's a 7 followed by 27 zeros, a number so vast it's difficult to truly comprehend. Each breath you take contains atoms that were once breathed by people who lived thousands of years ago. Some of those atoms were in the lungs of Leonardo da Vinci, Cleopatra, or the first humans to paint on cave walls. Atoms connect us all, across time and space, through history and prehistory. But atoms themselves, despite being incredibly small, are made of even smaller things. At the center of each atom is a dense nucleus, and around this nucleus, like planets in extremely distant orbits around a sun, move electrons. These electrons are extraordinarily light. It would take 2,000 electrons to equal the weight of a single proton in the nucleus. An electron is so light that if you could somehow hold one in your hand, you wouldn't feel its weight at all. The space between the nucleus and the electrons is vast, almost incomprehensibly so. If an atom were enlarged to the size of a football stadium, the nucleus would be a marble sitting at the center of the field, and the electrons would be tiny grains of sand floating somewhere in the highest seats. The rest, the vast majority of the atom, would be empty space. You are mostly empty space. The chair supporting you is mostly empty space. The earth beneath you, for all its solidity, is mostly empty space. And yet, here we are, solid and real, unable to fall through the floor or phase through walls. This is where quantum physics begins, in this realm of the incredibly small, where the rules are utterly different from everything we experience in our daily lives. In the quantum world, common sense fails. Intuition misleads. The impossible becomes routine, and the routine becomes impossible to truly understand. Light and energy. Light is one of nature's most beautiful mysteries, something we experience every moment our eyes are open, yet something we rarely stop to truly consider. For centuries, brilliant minds debated what light truly was. Is it a wave, like ripples spreading across a pond when you drop a stone? Or is it a stream of particles, like rain falling from the sky, each droplet discrete and separate? The answer, as quantum physics reveals, is both. And neither. Light behaves as both wave and particle, depending on how we look at it. This sounds impossible. How can something be two fundamentally different things? But nature doesn't care about our categories or our logic. When we're not observing light, when it's traveling through space, it behaves as a wave. But when light interacts with matter, when it hits your eye, strikes a solar panel, or is absorbed by a leaf during photosynthesis, it arrives as tiny packets of energy called photons. Each photon is a quantum of light. The word quantum simply means a discrete amount, a specific packet that cannot be divided. You cannot have half a photon, just as you cannot have half a marble or half an electron. Energy, at its smallest scale, comes in these indivisible chunks. This was one of the first great discoveries of quantum physics, made by Max Planck in 1900 when he was trying to understand why hot objects glow the colors they do. Different colors of light have different energies. Blue light photons carry more energy than red light photons. This is why blue light from screens can feel more stimulating to your brain, while red light feels calmer, softer. The sunset's red glow is nature's way of gently preparing the world for sleep, bathing everything in low-energy photons that don't trigger alertness in the same way the blue sky of midday does. Everything glows, in its own way. Even you, right now. Your body emits infrared light, heat, as photons radiating away into the darkness. These invisible photons carry the warmth of your metabolism, the heat of life, out into the cooler air around you. Right now, photons are leaving your skin, carrying away the day's warmth, preparing you for rest. You are a soft lantern of infrared light, glowing gently in the dark. The speed of light, about 186,000 miles per second, is not just fast. It's the universe's speed limit, the maximum speed at which anything can travel, at which information can move from one place to another. Light doesn't just happen to go this fast. The speed of light is woven into the structure of space-time itself, a fundamental constant of nature. Every photon, whether from a candle flame or a distant quasar billions of light-years away, travels at exactly this speed. Level 3 wave-particle duality. Let's explore deeper into this strange duality, this impossible both and neither nature of quantum objects. Imagine standing at the ocean's edge, watching waves roll in. Each wave is continuous, spread out across the water, rising and falling in smooth curves. The wave doesn't exist in one place, it's extended, distributed, a pattern moving through the medium of water. Now imagine someone throwing pebbles into the water. Each pebble is discrete, separate, individual. It has a definite location, a specific trajectory. It's here, not there. Quantum particles are somehow both. An electron, for instance, isn't really a tiny ball orbiting the nucleus, even though we often picture it that way for simplicity. It's more like a cloud of probability, a wave of potential, spread throughout space. The electron doesn't have a definite position until something measures it, interacts with it, asks the universe, where is the electron? Only when we measure it, when we look for it, does it appear as a particle in a specific location. This isn't a limitation of our measuring tools, as if we're just not clever enough to detect where the electron really is without disturbing it. It's fundamental to reality itself. Before measurement, the electron genuinely doesn't have a definite position. It exists in multiple places simultaneously, in a state called superposition. The very act of observation collapses this spread-out wave into a single point. Reality crystallizes under the gaze of measurement. Think of it like a musical note. Before you play a piano key, the note exists as potential in the taut string. When you strike the key, the string vibrates, creating a wave that spreads through the air in all directions. That wave is extended, distributed, not located in one place. But when that wave reaches your ear, when it vibrates your eardrum and triggers nerves, it becomes a discrete sensation, a specific note, at a specific moment, heard by you. The wave becomes an experience, the distributed becomes the definite. In the quantum world, reality itself works this way. Particles exist as waves of possibility until observation crystallizes them into definite states. The universe, at its most fundamental level, is far more fluid, far more open, far more participatory than it appears. We are not passive observers of a fixed reality. We are participants in its continual creation. Louis de Broglie proposed in 1924 that if light waves can behave as particles, then perhaps matter particles can behave as waves. He was right. Every particle has an associated wavelength, inversely proportional to its momentum. For large objects like baseballs or planets, this wavelength is unimaginably small, which is why we never see them behaving as waves. But for tiny particles like electrons, the wavelength is significant, and wave behavior becomes obvious. Level 4, the uncertainty principle. Werner Heisenberg, a young physicist in his 20s, discovered something profound in 1927 that would forever change our understanding of knowledge itself. He found that there are fundamental limits to what we can know about quantum particles. Not because our instruments aren't good enough, not because we're clumsy experimenters, but because certainty itself has limits at the quantum scale. The uncertainty principle states that you cannot simultaneously know both the exact position and exact momentum of a particle. The more precisely you measure where something is, the less you can know about where it's going and how fast. The more precisely you measure its speed and direction, the less you can know about its location. Position and momentum are complementary properties. Knowing one with perfect precision makes the other completely uncertain. It's as if reality itself is slightly blurred at the smallest scales, like trying to focus a camera on something very close to the lens. You can make one part sharp, but then another part necessarily goes fuzzy. Nature has a built-in fuzziness, a fundamental uncertainty woven into the fabric of existence. This isn't a bug in the universe's programming, it's a feature, an essential characteristic of quantum reality. This isn't just a quirk of particles, an oddity of the subatomic world that doesn't affect us. It's a statement about information, knowledge, and the nature of reality. There are questions that, even in principle, cannot be answered. Not because we lack the technology, not because we haven't been clever enough, but because the universe itself doesn't contain those answers until the moment of measurement. The future is not encoded in the present in the deterministic way we once imagined. There's a similar uncertainty between energy and time. The more precisely you know when something happened, the less you can know about the energy involved. For very short time intervals, energy becomes very uncertain. This allows, as we'll see later, particles to briefly borrow energy from nothing, violating what we think of as energy conservation for fleeting moments. In a strange way, this is comforting. Even the universe doesn't have everything figured out in advance. There's spontaneity, openness, genuine uncertainty in the cosmos. Not everything is predetermined, marching toward an inevitable future encoded in the initial conditions. At the quantum level, the future is genuinely open, undecided, waiting to be created by the countless measurements and interactions happening every moment. Heisenberg once reflected that nature allows us to answer only certain combinations of questions, not all questions simultaneously. Nature has secrets it will never reveal, not because it's hiding them, but because those secrets don't exist until we force nature to choose. Level 5, Quantum Tunneling. Here's something that would be completely impossible in the everyday world we experience, yet happens countless trillions of times in your body every second you're alive. Quantum tunneling allows particles to pass through barriers they shouldn't be able to cross, to appear on the other side of walls that should be impenetrable. Imagine rolling a ball toward a hill. If the ball doesn't have enough energy to reach the top, it rolls back down. It cannot magically appear on the other side of the hill. The laws of classical physics absolutely forbid it. But quantum particles can do exactly this. They can tunnel through energy barriers, appearing on the other side even when they don't have enough energy to go over the top. This happens because of that wave nature we discussed. The wave describing a particle doesn't stop abruptly at a barrier like water hitting a dam. Part of the wave extends slightly into and through the barrier, like a whisper seeping under a door. Most of the time, when you measure the particle, you find it bounced back, just as you'd expect. But occasionally, and these statistics can be calculated precisely, the particle appears on the other side, having tunneled through the supposedly impenetrable barrier. The sun shines because of quantum tunneling. In the sun's core, temperatures reach about 15 million degrees Celsius. At these temperatures, hydrogen nuclei slam together with tremendous violence. But hydrogen nuclei are positively charged, and like charges repel each other with tremendous force. The nuclei are surrounded by energy barriers created by this electromagnetic repulsion. Classically, the nuclei don't have enough energy to overcome these barriers and get close enough to fuse together. Yet fusion happens. Hydrogen nuclei tunnel through the electromagnetic barriers, get close enough for the strong nuclear force to grab them, and fuse into helium, releasing enormous amounts of energy in the process. Every photon warming your face on a sunny day exists because of quantum tunneling that happened in the sun's core millions of years ago. That's how long it takes photons to random walk from the core to the surface. In your cells, right now, electrons are tunneling through barriers in the intricate molecular machinery of respiration. The very energy powering your thoughts, your heartbeat, your breathing right now, all of it depends on quantum tunneling. Your consciousness is made possible by impossibilities happening constantly at the quantum scale. You are alive because particles in your cells routinely do things that shouldn't be possible. Quantum tunneling explains radioactive decay. An alpha particle, 2 protons and 2 neutrons bound together, sits inside a heavy nucleus, trapped by nuclear forces. It doesn't have enough energy to escape. But it can tunnel out, and eventually, randomly, it does. This is why radioactive decay is probabilistic. We can't predict when a specific atom will decay, only the probability of decay over a given time. Level 6, Electron orbitals. Let's return to the atom and look more carefully at those electrons orbiting the nucleus. Except they're not really orbiting, not like planets around a sun. That early model of the atom, proposed by Niels Bohr, was a useful approximation but not quite right. The reality is stranger and more beautiful. Electrons exist in what we call orbitals, regions of space where they're likely to be found. An orbital is a quantum state, a solution to the Schrödinger equation that describes how quantum systems evolve. It's defined by a set of numbers, quantum numbers, that describe the electron's energy, its angular momentum, its spatial orientation, and its spin. Each orbital has a distinctive shape. The simplest, called s orbitals, are spherical, like fuzzy balls centered on the nucleus. The next simplest, p orbitals, are dumbbell-shaped, with 2 lobes pointing in opposite directions. Then there are d orbitals, f orbitals, each with increasingly complex and beautiful shapes, like sculptures made of probability. But here's the key, the part that's truly quantum: an electron in an orbital doesn't move around within that space like a planet in orbit, tracing out a path. Instead, it exists simultaneously throughout the entire orbital, as a cloud of probability. The cloud is denser where the electron is more likely to be found if you measure it, more diffuse where it's less likely. But before measurement, the electron is spread throughout the entire space, not located anywhere in particular. When an electron absorbs energy, from light, for instance, or from heat, it can jump to a higher orbital, farther from the nucleus. This happens instantaneously, in quite literally no time at all. The electron doesn't travel through the space between orbitals like a ball thrown from one person to another. It simply ceases to exist in one orbital and begins existing in another. This is called a quantum leap, and it's the origin of that phrase we now use to mean any sudden, dramatic change. When the electron falls back down to a lower orbital, it releases the energy difference as a photon of light. The color of that light, its frequency, its energy, depends precisely on the size of the jump, on the energy difference between the 2 orbitals. This is why different elements glow with different colors when heated. Sodium produces yellow light, copper produces green, strontium produces red. Each element has its own unique set of possible jumps, its own quantum signature written in light. This is how we know what distant stars are made of. We look at the light they emit, see which colors are present and which are missing, and from this we can deduce their composition. The same quantum mechanics that governs atoms in laboratories here on Earth also governs atoms in galaxies billions of light years away. The laws of quantum physics are universal, the same everywhere and everywhen. Level 7, Spin and the Pauli exclusion principle. Electrons have a property called spin, and despite the name, they're not actually spinning like a top or a planet. Spin is an intrinsic form of angular momentum that has no classical analog whatsoever. It's a purely quantum property, something that exists only in the quantum realm and has no corresponding phenomenon in the everyday world we experience. Spin comes in two varieties for electrons, which we call spin up and spin down. You can think of these as two different orientations, like a coin showing heads or tails, or like an arrow pointing either up or down. But remember, until we measure the spin, an electron exists in a superposition of both spin states simultaneously. It's not that we don't know whether it's spin up or spin down, it genuinely is both, hovering in quantum limbo until observation forces it to choose. Wolfgang Pauli, a brilliant and notoriously critical physicist, discovered a crucial rule in 1925: no two electrons in an atom can have the same set of quantum numbers. They must differ in at least one property: energy level, orbital type, spatial orientation, or spin. This is the Pauli exclusion principle, and it's the reason matter is stable, the reason you don't fall through your chair, the reason chemistry works the way it does. Because of this principle, electrons fill atomic orbitals in a specific order, like people filling seats in a theater. The first electron can be in the lowest energy orbital with spin up. The second electron can also be in the lowest orbital, but only if it has spin down. It must differ in at least one quantum number. The third electron finds the lowest orbital fully occupied, so it must move to a higher energy orbital. This principle explains the entire structure of the periodic table of elements. Elements in the same column have similar chemical properties because they have the same number of electrons in their outermost orbitals. Hydrogen and lithium, sodium and potassium, they behave similarly because their outer electrons occupy similar configurations. The beautiful order of the periodic table emerges entirely from the Pauli exclusion principle combined with the mathematics of quantum mechanics. This principle explains chemistry itself. Atoms bond together to form molecules because they can lower their energy by sharing electrons, filling their orbitals in more stable configurations. Carbon forms four bonds because it has four electrons in its outer orbital, each seeking a partner. Oxygen forms two bonds. Hydrogen forms one. The fact that you are a complex, structured being rather than a collapsed blob of matter, you owe this to the Pauli exclusion principle. It also explains why solid matter is solid. When you sit on a chair, you don't fall through because the electrons in your body and the electrons in the chair repel each other. Not just because like charges repel electromagnetically, but because the Pauli exclusion principle forbids the electrons to occupy the same states. They cannot interpenetrate, cannot merge. This quantum mechanical repulsion is far stronger than ordinary electromagnetic forces at small distances. The exclusion principle applies to all fermions, particles with half-integer spin. This includes not just electrons but also protons, neutrons, and quarks. It's why neutron stars can support themselves against gravitational collapse. Neutrons, squeezed together to incredible densities, resist further compression because the Pauli exclusion principle forbids them to occupy the same quantum states. The star is held up by quantum mechanics itself. Level 8. Quantum entanglement. Now we come to what Einstein famously called spooky action at a distance, quantum entanglement. This is perhaps the most counterintuitive, most profoundly strange, and most philosophically significant phenomenon in all of physics. When two particles interact in certain ways, they can become entangled. After entanglement, they form a single quantum system, even though they may be physically separated. They're no longer independent entities but aspects of a unified whole. Even if you separate these particles by vast distances, even if you send one to the other side of the galaxy, they remain connected in a deep, fundamental way. Measure the state of one particle, and you instantly know the state of the other. Not because the measurement revealed information that was already there, but because the measurement of one particle instantaneously affects the state of the other. Change one, and the other changes correspondingly, faster than light could travel between them. The particles are not independent entities. They are aspects of a single, unified quantum state, no matter how far apart they appear to be. This isn't telepathy or magic or science fiction. No information can be transmitted faster than light using entanglement. The speed of light remains the universe's speed limit for sending messages. But entanglement reveals something deep and unsettling about the nature of reality. Separation is, in a fundamental sense, an illusion at the quantum level. Two particles that have interacted retain a connection that transcends space, that exists outside the ordinary structure of space-time. Einstein found this deeply troubling. In 1935, he and his colleagues Boris Podolsky and Nathan Rosen published a paper arguing that quantum mechanics must be incomplete. Einstein believed in local realism, the idea that objects have definite properties independent of observation, and that influences cannot travel faster than light. Entanglement seemed to violate one or both of these principles. Einstein proposed that there must be hidden variables we haven't discovered yet, additional information beyond the quantum wave function, which would restore common sense to the quantum world. But experiments have shown that Einstein was wrong about this. In the 1960s, physicist John Bell derived mathematical inequalities that any local hidden variable theory must satisfy. Beginning in the 1970s and continuing to the present, increasingly sophisticated experiments have tested Bell's inequalities. The verdict is clear: hidden variable theories have been ruled out. The universe really is as strange as quantum mechanics suggests. Entanglement is real. The world is fundamentally non-local. Particles separated by any distance can be correlated in ways that defy our deepest intuitions about space and separation. The universe is more deeply interconnected than we ever imagined. Nothing is truly separate from anything else. Everything that has ever interacted remains, in some sense, one thing. This connection persists not just across space but, in a sense, across time. When you observe an entangled particle now, you affect not just its distant partner but also the past moment when they became entangled. The quantum world is not just non-local in space but temporally non-local as well. Past, present, and future are more intertwined than our everyday experience suggests. Level 9, Quantum Superposition. Superposition is perhaps the defining feature of quantum mechanics, the characteristic that makes the quantum world fundamentally different from the classical world we experience. Before measurement, before observation, a quantum system exists in all its possible states simultaneously. Not in one state or another, but in all of them at once. A particle can be in multiple places at once, occupying several positions simultaneously. An atom can be in multiple energy states at once, both excited and unexcited until someone checks. A quantum system can be here and there, now and then, this and that, all at the same time. Reality, at the quantum level, is a shimmering superposition of possibilities, collapsing into definite actuality only under the gaze of measurement. The famous thought experiment of Schrödinger's cat illustrates this strangeness, though it was intended as a criticism of quantum mechanics. Place a cat in a sealed box with a quantum device, say, a radioactive atom that has a 50% chance of decaying within an hour. If the atom decays, it triggers a mechanism that releases poison, killing the cat. If it doesn't decay, the cat lives. Now, according to quantum mechanics, until you open the box and observe, the atom is in superposition of decayed and not decayed. The quantum system hasn't decided yet. And if the atom is in superposition, then so is the entire chain of events it triggers. The poison is both released and not released. And therefore, the cat is both alive and dead simultaneously, hovering in quantum limbo until you open the box and look. Of course, real cats don't exist in superposition of alive and dead. Cats are far too large, far too connected to their environment, for quantum behavior to persist. The quantum behavior disappears, decoheres, long before it reaches the scale of cats. But the thought experiment highlights how radical superposition is. It's not multiple qubits in superposition can explore vast numbers of possibilities in parallel, all at once. While a classical computer must check each possibility sequentially, one after another, a quantum computer can check many possibilities simultaneously. Nature has been using quantum superposition for billions of years. Photosynthesis, the process by which plants convert sunlight into chemical energy, involves quantum superposition. When a photon is absorbed by a chlorophyll molecule, the energy explores multiple pathways through the molecular machinery simultaneously, finding the most efficient route with nearly perfect efficiency. Plants have been doing quantum computing since long before humans appeared on Earth. Birds may use quantum superposition for navigation. Their eyes contain molecules that become entangled when struck by light. The entanglement is affected by Earth's magnetic field, allowing the birds to literally see magnetic field lines. This quantum sense helps them navigate across continents during migration. The European robin, a small bird weighing barely an ounce, may be a quantum sensor more sophisticated than any technology we've built. Level 10, Decoherence. If quantum superposition is so fundamental, why don't we see it in everyday life? Why do cats appear either alive or dead, never both? Why do chairs exist in definite locations instead of quantum clouds of probability? Why does the quantum world of superposition and uncertainty give way to the classical world of definite states and predictable behavior? The answer is decoherence, a process discovered and understood only relatively recently in the history of quantum mechanics. Quantum systems are incredibly fragile. They maintain their superposition only as long as they remain isolated from their environment. But true isolation is nearly impossible, especially for anything larger than a few atoms. Air molecules bump into objects constantly. Light strikes them, photons bouncing off and carrying away information about the object's state. Thermal vibrations shake every atom. Each interaction entangles the quantum system with the environment. The superposition doesn't collapse in the sense of disappearing. Instead, it spreads outward, becoming entangled with more and more environmental particles. This entanglement dilutes the superposition across countless environmental particles, spreading it so thin that it becomes undetectable. The original system appears to collapse into a definite state, not because superposition has actually gone away, but because it's become so dispersed, so entangled with the environment, that we can't see it anymore. The quantum behavior has decohered into apparent classical behavior. This is why quantum effects are easy to observe in single atoms or small molecules but vanish for objects we can see with our eyes. Larger objects interact with their environment in too many ways, too quickly. A single molecule might maintain superposition for seconds or even minutes under the right conditions. A dust mote, barely visible, decoheres in less than a nanosecond. A cat would decohere in less time than it takes light to cross an atom. Decoherence explains the boundary between the quantum world and the classical world we experience. It's not a sharp line but a gradient, a transition region. Quantum behavior fades gradually as systems become larger and more connected to their surroundings. The classical world we experience emerges from the quantum world through decoherence, like a photograph developing from a chemical bath. Fighting decoherence is the central challenge in building quantum computers. To maintain quantum behavior long enough to perform useful calculations, systems must be cooled to near absolute zero, mere thousandths of a degree above the coldest temperature possible. They must be shielded from magnetic fields, vibrations, and stray light. Even with these precautions, quantum states typically last only microseconds or milliseconds before decoherence destroys them. The environment acts like a constantly watching observer, measuring the quantum system through countless tiny interactions. Each photon bouncing off, each air molecule colliding, each thermal vibration, All of these are miniature measurements, extracting information and destroying superposition. To maintain quantum behavior, you must isolate the system from every possible measurement channel, every possible source of information leakage. In a profound sense, decoherence explains why we see a definite, classical world at all. The universe is constantly observing itself, measuring itself through the interactions between its parts. Our experience of definite outcomes, of a world with chairs in specific locations and cats in definite states, emerges from the universal process of environmental decoherence. Level 11, the double-slit experiment. No exploration of quantum physics would be complete without discussing the double-slit experiment, perhaps the most beautiful, most bewildering, and most philosophically profound experiment in all of science. Richard Feynman called it a phenomenon which is impossible, absolutely impossible, to explain in any classical way, and which has in it the heart of quantum mechanics. The setup is simple. Send light through two narrow slits onto a screen behind them. What do you see? An interference pattern, alternating bright and dark bands. The bright bands occur where light waves from the two slits arrive in phase, reinforcing each other. The dark bands occur where they arrive out of phase, cancelling each other. This proves light is a wave. Now send light so dim that only one photon passes through the apparatus at a time. You'd expect each photon to go through one slit or the other, producing two bright spots on the screen where particles accumulate behind each slit. But this isn't what happens. Astonishingly, the interference pattern still builds up, photon by photon. Over time, thousands of individual particle detections create the characteristic wave interference pattern. Each single photon somehow interferes with itself. It behaves as if it passes through both slits simultaneously, even though it's a single, indivisible quantum of energy. The photon exists in superposition, taking both paths at once, and the two paths interfere to create the pattern we see. But if you place detectors at the slits to see which one each photon goes through, the interference pattern vanishes completely. With observation, with measurement, each photon goes through one slit or the other, behaving like a particle. The interference pattern, proof of wave behavior, disappears. Without observation, without measurement, each photon goes through both slits, behaving like a wave. The experiment works the same way with electrons, with atoms, even with large molecules containing hundreds of atoms. Matter exhibits the same wave-particle duality as light. Everything has this dual nature. You have an associated wavelength, though it's far too small to ever observe because you're so massive compared to quantum particles. The double-slit experiment reveals something profound. The act of measurement fundamentally changes the behavior of the system. Not just in the sense that observing something perturbs it slightly, but in a deep way. Whether you measure which slit the particle goes through determines whether the particle goes through one slit or both. The observer plays a role in creating the reality they observe. Even more strangely, it doesn't matter when you make the measurement. Delayed choice experiments show that you can decide whether to measure which slit the particle went through after the particle has already passed through the slit but before it reaches the screen. Your future choice affects the particle's past behavior. It went through both slits or one slit depending on a choice you haven't made yet. This isn't time travel in the science fiction sense. No information travels backward in time. But it reveals that the past isn't as fixed, as definite, as we imagine. The past crystallizes into definite actuality through measurements made in the present. History itself has an element of quantum uncertainty. Level 12, Quantum Field Theory. As we go deeper into quantum physics, as we seek a more fundamental description of reality, we discover that particles aren't really particles at all, they're excitations in quantum fields. This is quantum field theory, our most comprehensive and accurate description of the physical world, the theoretical framework that underlies the standard model of particle physics. A field is something that has a value at every point in space and time. The temperature in a room is a field, it has a specific value everywhere, varying smoothly from place to place. In quantum field theory, every type of particle has an associated field permeating all of space, extending throughout the universe. An electron is not a tiny ball or point. It's a localized excitation, a wave packet, in the electron field. A photon is an excitation in the electromagnetic field. A quark is an excitation in a quark field. The field is primary, fundamental, particles are secondary phenomena, like ripples on the surface of a deep ocean. The ocean is always there, and ripples come and go. These fields are not classical, smooth fields like temperature or air pressure. They're quantum fields, subject to uncertainty and superposition. Even in empty space, a perfect vacuum with no particles present, the fields are never truly still. They fluctuate, boiling with quantum uncertainty, creating temporary virtual particles that pop into and out of existence too quickly to be directly observed. These vacuum fluctuations are not mathematical abstractions or calculation tricks. They have measurable, physical effects. They cause a subtle shift in the energy levels of atoms called the Lamb shift, discovered in 1947 and one of the first precise confirmations of quantum field theory. They create a force between parallel conducting plates called the Casimir effect. The vacuum itself pushes the plates together. Empty space is not empty. It seethes with quantum activity. All forces arise from fields exchanging particles. Electromagnetism comes from exchanging photons between charged particles. The electromagnetic field connects every electron in the universe to every other electron through a web of virtual photon exchanges. The strong nuclear force holding atomic nuclei together comes from exchanging gluons between quarks. Even mass, the resistance to acceleration that seems so fundamental, comes from particles interacting with the Higgs field, acquiring mass in the process. The Higgs field is particularly remarkable. It's a field that has a non-zero value everywhere in space, even in a vacuum. Other particles moving through this field interact with it, and this interaction manifests as mass. Particles that interact strongly with the Higgs field are heavy. Particles that interact weakly are light. Photons don't interact with the Higgs field at all, which is why they're massless and travel at the speed of light. Quantum field theory describes the world with breathtaking precision. The magnetic moment of the electron, a measure of how strongly it interacts with magnetic fields, has been calculated using quantum field theory and measured experimentally. Theory and experiment agree to 11 decimal places, making it the most precisely confirmed prediction in all of science. Reality follows quantum field theory's equations with extraordinary fidelity. Level 13. Antimatter. Quantum field theory predicted something extraordinary that sounds like pure science fiction but is absolutely real. For every particle, there exists an antiparticle with opposite charge but otherwise identical properties. This is antimatter, and it's one of the most remarkable predictions of 20th century physics. The antiparticle of the electron is the positron, identical in mass and spin, opposite in charge. When an electron and positron meet, they annihilate each other completely, converting their mass entirely into energy according to Einstein's famous equation E equals mc squared. The mass literally becomes light, pure energy, photons carrying away the sum of the particles' rest masses. This isn't theoretical speculation. Antimatter is real and has been extensively studied in laboratories around the world. Positron emission tomography, PET scans used in hospitals, relies on positrons created by radioactive decay. When these positrons encounter electrons in your body, they annihilate, producing gamma rays that are detected to create images of internal organs and metabolic processes. Medical imaging routinely uses antimatter. Antimatter is produced naturally in cosmic ray collisions in the upper atmosphere. High-energy particles from space strike air molecules, creating showers of particles including antimatter. Some of these antimatter particles reach the ground. Right now, antiparticles are passing through your body, though far too few to cause any harm. Antimatter was abundant in the early universe. In the first moments after the Big Bang, when the universe was unimaginably hot and dense, particle-antiparticle pairs were constantly created and destroyed. Matter and antimatter existed in nearly equal amounts, in a roiling sea of creation and annihilation. But here's one of the great mysteries of physics. Why does our universe contain matter rather than antimatter? The Big Bang should have created exactly equal amounts of both. As the universe cooled, matter and antimatter should have mutually annihilated, leaving only light. Yet here we are, made of matter, living in a universe filled with matter, galaxies, stars, planets, all made of particles, not antiparticles. There must be some subtle asymmetry, some tiny difference in how matter and antimatter behave, that caused a slight excess of matter in the early universe, about one extra matter particle for every billion matter-antimatter pairs. Most particles annihilated, but that tiny excess survived. That excess became everything we see, all the galaxies, all the stars, all the atoms in your body. This asymmetry has been observed in particle physics experiments. Certain particles decay in slightly different ways than their antiparticles do, violating a symmetry called CP symmetry. But the observed asymmetries aren't large enough to explain the matter-antimatter imbalance in the universe. There must be additional sources of asymmetry we haven't discovered yet. Why does anything exist at all? Why is there something rather than nothing? The answer lies somewhere in the quantum behavior of matter and antimatter in the first moments after the Big Bang, in subtle violations of symmetry that we're still working to understand. Every atom in your body exists because of physics we don't yet fully comprehend. Level 14, the quantum vacuum. Let's look more carefully at the vacuum, at the empty space, because it turns out to be far from empty. The uncertainty principle tells us that energy and time are related in the same way position and momentum are. The more precisely a system has a definite energy, the longer that energy must exist. But this relationship can be inverted. For very short times, energy can be very uncertain. This means that for brief moments, energy can fluctuate by large amounts without violating any physical laws. The universe can briefly borrow energy from nothing, as long as it pays it back quickly enough. The shorter the time, the larger the energy fluctuation that's allowed. This leads to one of the strangest features of quantum reality. Particle-antiparticle pairs can spontaneously appear from nothing, borrow energy from the vacuum, exist for a fleeting moment, and then annihilate back into nothing. These are virtual particles, not directly observable because they exist for too short a time, but affecting everything around them in measurable ways. Virtual particles cannot be directly observed. They exist for too short a time, less than the time it would take light to cross their own diameter. But their effects are everywhere. They surround every real particle in a cloud, constantly appearing and disappearing. This cloud screens the particle's properties. The measured mass and charge of an electron include the contributions of its surrounding cloud of virtual particles. At smaller and smaller distances, if you could probe closer and closer to a particle's core, you would measure different values for its charge and mass. The particle's bare properties are different from its dressed properties that include the virtual particle cloud. What we observe is always the dressed particle, never the bare one. The vacuum is not a void but a potentiality. It's filled with every possible fluctuation, every possible particle-antiparticle pair, flickering in and out of existence in patterns too rapid and too small to directly observe. The vacuum is a seething foam of quantum activity at the smallest scales, what physicist John Wheeler called quantum foam. Near the event horizon of a black hole, these vacuum fluctuations have a dramatic consequence. Occasionally, a virtual pair forms with one particle inside the event horizon and one outside. They cannot come back together to annihilate. The outside particle becomes real, escaping as radiation. The inside particle falls into the black hole, reducing its mass. This is Hawking radiation, discovered by Stephen Hawking in 1974. Hawking radiation means black holes slowly evaporate. They're not eternal prisons from which nothing escapes. They radiate energy, lose mass, and eventually disappear completely in a final burst of radiation. For large black holes like those in galactic centers, this process takes unimaginably long, far longer than the current age of the universe. But small black holes, if any exist, would evaporate relatively quickly. Even empty space has an energy, the vacuum energy or zero-point energy. Every quantum field, even in its lowest energy state, has residual energy from these vacuum fluctuations. This energy is present everywhere in space. When you add up the contributions from all the fields, you get a number, the energy density of the vacuum itself. This vacuum energy may be what we observe as dark energy, the mysterious force accelerating the expansion of the universe. The vacuum itself, seething with quantum fluctuations, may be pulling the cosmos apart, causing galaxies to recede from each other at ever-increasing speeds. The fate of the universe may be determined by the quantum properties of empty space. However, there's a problem, perhaps the biggest problem in theoretical physics. When we calculate the vacuum energy using quantum field theory, we get a number that's absurdly large, about 10 to the power of 120 times larger than the observed dark energy. This is the worst prediction in the history of physics. Something is wrong with either our calculation or our understanding, and we don't know what. Level 15, Quantum Chromodynamics. Inside the nucleus of every atom, protons and neutrons are held together by the strong nuclear force, overcoming the electromagnetic repulsion between the positively charged protons. This force is described by quantum chromodynamics, or QCD, a quantum field theory with properties unlike any other force in nature. Protons and neutrons are not fundamental particles. They're composite, made of smaller constituents called quarks. Each proton contains 2 up quarks and 1 down quark. Each neutron contains 2 down quarks and 1 up quark. These quarks are held together by the strong force, bound so tightly that they can never be separated. Quarks come in 6 types, called flavors: up, down, strange, charm, bottom, and top. These names are whimsical and arbitrary. They have nothing to do with actual taste, strangeness, or charm. They're just labels for different types of quarks with different masses and properties. The up and down quarks are the lightest and make up ordinary matter. The others are heavier and unstable, decaying rapidly into lighter quarks. But quarks also have another property called color charge. This has nothing to do with actual color. It's a quantum property analogous to electric charge, but more complex. While electric charge comes in 2 types, positive and negative, color charge comes in 3 types, playfully called red, green, and blue. Antiquarks have anti-color charges: anti-red, anti-green, and anti-blue. The strong force is mediated by particles called gluons, which carry color charge themselves. This is profoundly different from electromagnetism. Photons, which carry the electromagnetic force, are electrically neutral. But gluons carry color charge, which means gluons can interact with other gluons. This self-interaction gives the strong force its unique properties. Here's where it gets truly strange. The strong force has an unusual property called asymptotic freedom. It doesn't weaken with distance as other forces do. Instead, it remains roughly constant and can even get stronger. Try to pull 2 quarks apart, and the force between them increases, like stretching an elastic band that gets stiffer the more you stretch it. If you pull hard enough, trying to separate the quarks, you don't get free quarks. Instead, the energy you've added creates new quark-antiquark pairs from the vacuum. The quarks remain confined, always bound in groups. No quark has ever been observed in isolation, and theoretical work suggests they never can be. This is called confinement, and it's why we never see free quarks, only protons, neutrons, and other composite particles. At high energies or temperatures, like those in the early universe fractions of a second after the Big Bang, or inside colliding particles at accelerators like the Large Hadron Collider, quarks become asymptotically free. The strong force weakens, and quarks behave almost as if they're not interacting. The universe was once a quark-gluon plasma, a hot soup of unconfined quarks and gluons. But as the universe cooled, as the temperature dropped below about 2 trillion degrees, quarks condensed into protons and neutrons. This phase transition, from quark-gluon plasma to confined nuclear matter, happened about a microsecond after the Big Bang. Before this transition, there were no protons or neutrons, no atomic nuclei, no possibility of atoms or chemistry or life. Everything that followed, atoms, stars, planets, life, depended on this moment when quarks became confined. Level 16, the Standard Model. All these pieces, quarks and leptons, photons and gluons, the Higgs field and antimatter, fit together in an elegant framework called the Standard Model of Particle Physics. It's our most comprehensive theory of matter and forces, describing 3 of the 4 fundamental forces and classifying all known elementary particles. The matter particles are fermions, particles with half-integer spin. They come in 2 categories, quarks and leptons. There are 6 quarks: up, down, strange, charm, bottom, and top. and 6 leptons, the electron, muon, and tau, each with an associated neutrino. These 12 particles, plus their antiparticles, constitute all the matter in the universe. These particles are organized in 3 generations or families. The first generation contains the up and down quarks and the electron and its neutrino. These are the lightest particles and make up ordinary matter. The second generation contains the charm and strange quarks and the muon and its neutrino. The third generation contains the top and bottom quarks and the tau and its neutrino. The heavier generations are unstable and decay into lighter ones. Why are there 3 generations? We don't know. 2 would be enough to build all the matter we see. Nature seems to repeat the same pattern 3 times at different mass scales, for reasons we don't understand. It's one of the deep puzzles the Standard Model cannot answer. The force particles are bosons, particles with integer spin. Photons carry electromagnetism, allowing atoms to form and light to exist. W and Z bosons carry the weak nuclear force, responsible for radioactive beta decay and crucial for nuclear fusion in stars. 8 gluons carry the strong force, binding quarks into protons and neutrons and nucleons into nuclei. And the Higgs boson, discovered in 2012, is associated with the Higgs field that gives particles mass. The Standard Model has been spectacularly successful. It's predicted countless phenomena, all confirmed by experiment to extraordinary precision. The anomalous magnetic moment of the electron, the masses of the W and Z bosons, the existence of the top quark, the properties of the Higgs boson, prediction after prediction has been verified. The discovery of the Higgs boson at the Large Hadron Collider was the final piece of the Standard Model, found exactly where the theory predicted, with the predicted properties. Yet for all its success, the Standard Model is incomplete. It doesn't include gravity. Einstein's general relativity describes gravity, but we don't know how to combine it with quantum mechanics. It doesn't explain dark matter, which makes up about 27% of the universe's mass energy but doesn't interact electromagnetically. It doesn't explain dark energy, the mysterious force accelerating cosmic expansion. The Standard Model doesn't explain why particles have the masses they do. The electron is about 200 times lighter than the muon, which is about 17 times lighter than the tau. The top quark is about 40,000 times heavier than the up quark. Why these particular values? The theory doesn't say. These masses must be measured experimentally. The theory doesn't predict them from deeper principles. There are about 20 parameters in the Standard Model, masses, coupling constants, mixing angles, that must be measured and input into the theory. Why these particular values rather than others? Are they fundamental constants of nature, or do they emerge from some deeper theory? We don't know. The Standard Model is a phenomenally successful description of nature, but clearly not the final word. Level 17, Quantum Interpretations. We've described what quantum mechanics predicts, the mathematical formalism and experimental results, but what does it all mean? What is actually happening when superposition collapses, when observation creates definite outcomes from quantum possibilities? This is the measurement problem, and physicists have proposed numerous interpretations, different ways of understanding the same mathematics. The Copenhagen interpretation, developed by Niels Bohr, Werner Heisenberg, and others in the 1920s, suggests that quantum mechanics is complete. The wave function describes everything that can be known. Before measurement, Particles don't have definite properties, they're in superposition. Measurement causes collapse, the transition from possibility to actuality. There's no deeper reality beneath the quantum description. This view was dominant for decades and remains widely held. But what counts as a measurement? What causes collapse? The Copenhagen interpretation doesn't give clear answers. Is a human observer required, or does any sufficiently large system count? Where exactly is the boundary between the quantum and classical worlds? These questions remain contentious. The many-worlds interpretation, proposed by Hugh Everett in 1957, takes a radically different approach. It suggests that superposition never collapses. Instead, every quantum possibility is realized in a branching multiverse. When you measure a particle's spin, the universe splits. In one branch, you observe spin up. In another branch, another version of you observes spin down. Both outcomes happen, just in different universes. In this view, there's no collapse, no special role for measurement. The wave function always evolves deterministically according to the Schrödinger equation. What we experience as collapse is just our branch of the universe becoming decorrelated from other branches. Other versions of you exist in parallel universes, experiencing different outcomes of quantum measurements. This interpretation seems extravagant, infinitely many universes created at every quantum event. But it's mathematically elegant, requiring no special collapse mechanism. The equations of quantum mechanics are taken completely literally, with no additional assumptions. Many physicists find this appealing, though it's experimentally indistinguishable from other interpretations. De Broglie-Bohm theory, or pilot wave theory, proposes that particles do have definite positions and momenta at all times, guided by a quantum pilot wave. The wave function is real, physically existing, but particles also have definite trajectories, deterministic paths through space. This restores classical determinism but requires accepting instantaneous, non-local connections throughout space. Changes to the wave function in one location instantly affect particle trajectories everywhere. Objective collapse theories propose that the wave function physically collapses due to gravity or other mechanisms, without requiring observation. These theories modify quantum mechanics slightly, predicting tiny departures from standard quantum predictions that might be experimentally testable. Perhaps quantum mechanics breaks down for sufficiently massive objects, with gravity causing spontaneous collapse. Cubism, or quantum Bayesianism, takes a subjective approach. Quantum states represent personal degrees of belief, not objective reality. When you measure a quantum system and update the wave function, you're updating your beliefs based on new information, not describing a physical collapse. Different observers can assign different quantum states to the same system, and that's okay. Quantum states are subjective, like probabilities in Bayesian statistics. Which interpretation is correct? We don't know. Experimentally, they're extremely difficult to distinguish. They make the same predictions for all observations we can currently perform. The choice between them is partly philosophical, a matter of what ontology, what view of reality's nature, you find most compelling. Do you prefer a single universe with irreducible randomness, or infinite deterministic universes? Objective reality or subjective knowledge? Physics alone cannot decide. Level 18, Quantum Information. Quantum mechanics has given rise to a new understanding of information itself. Information is physical. It has mass, energy, and entropy. It cannot be created or destroyed, only transformed. The laws of quantum mechanics place fundamental limits on how information can be stored, processed, and transmitted. A classical bit can be either 0 or 1. A qubit, quantum bit, can be in superposition of 0 and 1, existing as both simultaneously until measured. 2 qubits can be in superposition of 4 states, 0, 0, 0, 1, 10, and 11. 3 qubits can be in 8 states. N qubits can represent 2 to the power of n states at once. This exponential scaling gives quantum computers their potential power. For certain problems, quantum computers can dramatically outperform classical computers. Schia's algorithm can factor large numbers exponentially faster than the best-known classical algorithms, threatening current encryption systems. Grover's algorithm can search unsorted databases quadratically faster than classical search. Quantum simulations can model quantum systems efficiently, something classically intractable. But quantum computers aren't universally faster. For many problems, they offer no advantage. They're not better computers in a general sense, just different, able to exploit quantum parallelism for specific tasks. Building large-scale quantum computers remains enormously challenging due to decoherence and the difficulty of maintaining quantum states. Quantum entanglement enables quantum cryptography. 2 parties sharing entangled particles can communicate with perfect, provable security. Any eavesdropper trying to intercept the message would disturb the quantum states, revealing their presence. This isn't just computational security, relying on the difficulty of solving certain math problems. It's physical security, guaranteed by the laws of quantum mechanics. Quantum key distribution has been demonstrated over hundreds of kilometers through fiber optics and through space using satellites. Quantum teleportation allows the transfer of a quantum state from one location to another without the state traveling through the intervening space. Using entanglement and classical communication, you can make one particle assume the exact quantum state of another distant particle. The original state is destroyed in the process. You can't clone quantum information, but it's recreated elsewhere. Quantum teleportation has been demonstrated with photons, atoms, and even small collections of atoms. The no-cloning theorem states that you cannot create an identical copy of an arbitrary unknown quantum state. This isn't a technological limitation but a fundamental principle. It arises from the linearity of quantum mechanics, the fact that quantum evolution is described by linear operators. If cloning were possible, you could violate the uncertainty principle by making many copies and measuring complementary properties. The no-cloning theorem ensures the security of quantum cryptography. These insights reveal that information is perhaps more fundamental than matter or energy. Some physicists, following John Wheeler's slogan "It from bit," believe the universe itself is fundamentally informational, a vast quantum computer, with physical laws emerging from information-theoretic principles. Physical reality might be, at its deepest level, information processing. The holographic principle suggests that all the information in a volume of space can be encoded on its boundary, like a hologram. The three-dimensional world we experience might be a projection of information encoded on a two-dimensional surface. This idea comes from studying black holes and quantum gravity, and it hints that space itself might be emergent from quantum information. Quantum error correction, developed to protect quantum computers from decoherence, has deep connections to quantum gravity. The mathematics of error-correcting codes appears in descriptions of spacetime geometry. Perhaps spacetime itself is an error-correcting code, and the fundamental structure of the universe is informational. These are speculative ideas, but they suggest that understanding quantum information might be key to understanding reality at the deepest level. Level 19: Quantum Gravity. The greatest unsolved problem in theoretical physics is unifying quantum mechanics with general relativity, Einstein's theory of gravity. These two theories, both brilliantly successful in their domains, seem fundamentally incompatible. General relativity describes gravity as the curvature of spacetime. Quantum mechanics describes forces as exchanges of particles. How can spacetime be both a smooth, curved geometry and a quantum field with particle excitations? General relativity treats spacetime as continuous, smooth, dynamic. Mass and energy curve spacetime, and this curvature is gravity. Objects follow geodesics, straight lines in curved spacetime. The theory has been tested extensively and passed every test. It predicts black holes, gravitational waves, the expansion of the universe, all confirmed by observation. Yet it treats spacetime classically, not quantum mechanically. Quantum mechanics treats everything as discrete, uncertain, subject to superposition. Particles are excitations in quantum fields. Forces arise from exchanging particles. The theory has been tested to incredible precision and correctly describes all non-gravitational interactions. Yet it assumes spacetime is a fixed background, not a dynamic entity. At the Planck scale, about 10 to the power of -35 meters and 10 to the power of -43 seconds, both quantum effects and gravitational effects become strong. These are unimaginably small scales. The Planck length is to an atom what an atom is to the entire observable universe. At this scale, spacetime itself should fluctuate quantum mechanically, foaming and churning with quantum uncertainty. Our current theories break down completely at this scale. String theory proposes that fundamental particles are not point-like but tiny vibrating strings of energy. Different vibration patterns correspond to different particles. A string vibrating one way appears as an electron. Vibrating another way, it appears as a photon. Vibrating yet another way, it appears as a graviton, the hypothetical particle carrying gravity. This theory naturally includes gravity and unifies all forces in a single framework. But string theory requires extra spatial dimensions beyond the 3 we experience. The math only works in 10 or 11 dimensions. Where are the extra dimensions? The theory proposes they're compactified, curled up so small we can't observe them, like a garden hose appearing one-dimensional from far away but revealing its two-dimensional surface up close. The shape of these extra dimensions determines the properties of particles we observe, their masses, charges, and interactions. String theory has been criticized for making few testable predictions. There are countless ways to compactify the extra dimensions, leading to a vast landscape of possible universes with different physical laws. Which one describes our universe? The theory doesn't say. Without testable predictions that distinguish string theory from other theories, it remains speculative, though mathematically beautiful and profound. Loop quantum gravity takes a different approach, quantizing spacetime directly without requiring extra dimensions. Space is not continuous but made of discrete loops woven together in a network. These loops are quantum states of geometry itself, tiny loops of space about a Planck length in size. Space-time is built from these fundamental loops, like a fabric woven from threads. In loop quantum gravity, time itself emerges from changes in this network. Time is not fundamental but a way of describing how the network evolves, how loops reconnect and rearrange. Space and time are not the fundamental reality but emergent from something more basic, quantum geometry. This has profound implications. If time emerges, what does it mean for a theory to describe how things change? Other approaches include causal set theory, where space-time is a discrete set of points with causal relations between them, and space-time emerges from the structure of these causal relations. Emergent gravity theories propose that gravity isn't fundamental but emerges from quantum entanglement, like temperature emerging from molecular motion. Asymptotic safety suggests gravity remains a quantum field theory but becomes well-behaved at high energies through a special mathematical property. We don't know which, if any, of these approaches is correct. Quantum gravity might not be directly testable with current technology. The energies required to probe the Planck scale are unattainable in particle accelerators. We may need to observe indirect signatures in cosmology, imprints left on the cosmic microwave background radiation from the early universe, or subtle effects in black hole observations. Or perhaps we'll need entirely new ideas we haven't thought of yet. Level 20, the deepest questions. As we near the end of our journey, let's consider the deepest mysteries that quantum physics has revealed and the profound questions that remain unanswered. Let yourself drift with these questions, not trying to answer them but simply allowing them to wash over you. Why does quantum mechanics work? We can calculate with extraordinary precision. We can predict experimental outcomes correctly. We can build technologies based on quantum principles. But we don't truly understand why nature operates this way. Why superposition? Why uncertainty? Why does observation matter? These aren't questions physics can easily answer. They venture into philosophy, into metaphysics, into the nature of existence itself. Is consciousness related to quantum mechanics? Some have speculated that the quantum measurement problem and the nature of consciousness are linked, that observers are necessary to collapse superposition, and consciousness is what makes something an observer. Perhaps consciousness and quantum mechanics are two aspects of the same mystery. Most physicists are skeptical of this connection, but the question remains tantalizing, hovering at the boundary between physics and philosophy of mind. What is the universe's wave function? If quantum mechanics applies to everything, the entire universe should have a quantum state, a universal wave function evolving according to the Schrödinger equation. But what does measurement mean when there's nothing outside the system to measure it? Does the universe observe itself? These questions arise in quantum cosmology, where we try to apply quantum mechanics to the entire cosmos. Quantum mechanics suggests that reality is fundamentally relational and participatory. Things don't have properties in isolation but only in relation to other things, through interaction and measurement. The universe is not a collection of independent objects existing separately but a web of relationships, constantly creating each other through measurement and entanglement. Reality is participatory. We are not passive observers but active participants in the continual creation of the world we experience. At the deepest level, perhaps, the universe is made of information, possibility, and mathematics. Matter and energy are manifestations of abstract patterns, quantum fields vibrating in harmony with timeless mathematical laws. The universe is mathematical structure, and we are the universe contemplating itself. Quantum processes complex enough to wonder about quantum processes. And here's something beautiful to contemplate as you drift toward sleep. Every atom in your body was once part of a star. Stars forge heavy elements in their cores through nuclear fusion, processes governed by quantum mechanics. When stars explode as supernovae, they scatter these elements into space. New stars and planets form from this enriched material. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were created in stellar furnaces billions of years ago. Those atoms have existed for billions of years, cycling through countless forms. They've been in oceans, mountains, dinosaurs, flowers, clouds. They've been scattered and gathered, combined and separated, in endless transformations. Now they're briefly arranged as you, conscious and contemplating the quantum nature of existence. Soon they'll move on to other forms, other patterns, continuing their journey through the universe. Your thoughts arise from quantum processes in neurons. Neurotransmitters cross synapses through processes involving quantum tunneling. Ion channels in nerve cells may use quantum effects to enhance their sensitivity. Your perception of color comes from photons interacting with quantum systems in the retinal molecules of your eyes. Your sense of smell involves quantum shape recognition in olfactory receptors. Your very existence depends on quantum tunneling in cellular respiration. You are not separate from the quantum world. You are it, experiencing itself. The universe is far stranger, far more beautiful, and far more interconnected than our everyday experience suggests. Space and time, solidity and separation, cause and effect, these are approximations, useful fictions our minds construct from quantum reality. The classical world we experience emerges from the quantum world through decoherence, but underneath, the quantum nature remains. At the quantum scale, everything is connected. Particles that have interacted remain entangled across any distance. Every photon you've ever seen was once entangled with its source. Light from distant stars, traveling for thousands of years, still carries correlations with the atoms that emitted it in a stellar atmosphere long ago. Every breath connects you to the distant past. You are connected, through layer upon layer of past interactions, with everything. Every breath you take contains atoms from the first breath of every human who has ever lived. You're breathing atoms that were in Julius Caesar's last breath, in Buddha's first breath, in the first words ever spoken. You are breathing stardust, quantum fields arranged in the temporary pattern called you. Rest now. Let these thoughts dissolve like superposition collapsing into sleep. The quantum world continues its dance, particles and waves, here and there, now and then, all at once. Tomorrow you'll wake in this strange, beautiful quantum universe, and it will look ordinary again, solid and classical. But you'll know better. You'll know the extraordinary truth hidden in every moment, every atom, every heartbeat. The quantum realm is always here, beneath the surface of things, humming with possibility and connection. And you are part of it, made of it, inseparable from it. Your consciousness emerges from quantum processes in neurons. Your body is sustained by quantum tunneling in cells. Your very atoms were forged in quantum processes in stellar cores and bound together by quantum forces. Physics tells us that the universe is weirder than we can imagine, more interconnected than we can understand, more beautiful than we can fully appreciate. It tells us that reality is not as it seems, that the solid, separate, classical world is an illusion emerging from quantum reality. It tells us that we are participants in the universe's self-observation, part of how it comes to know itself. Rest well in this quantum cosmos. Let the uncertainty principle cradle you gently. You don't need to know everything, to understand everything, to measure everything. Some things can remain in superposition, in possibility, in the realm of potential. Let superposition hold you gently in all your possible states, the you that worries and the you that rests, the you that thinks and the you that dreams. Let entanglement connect you with everything that is, with all the people you love, with all the atoms you've shared breath with all the photons that have touched your skin, with the stars whose light has reached your eyes across vast distances and times. You are not alone. You are part of a vast quantum web connecting everything that is, was, and will be. Good night. Sleep peacefully in the knowledge that you are made of stardust and quantum fields, that you are the universe knowing itself, that you are connected to everything through layers of quantum entanglement stretching back to the Big Bang. You are a brief, beautiful pattern in the quantum field, conscious and wondering, part of the cosmos contemplating its own mystery. Rest now. The quantum world continues without you, but you are never truly separate from it. Tomorrow you'll return to it, conscious again, experiencing the classical illusion emerging from quantum reality. But tonight, simply rest. Let yourself dissolve into possibility, into the quantum foam from which all things arise. The universe is singing a quantum song, and you are one of its notes. Rest now. Let the music play. Remember to subscribe when you wake up. Good night.